You're listening to the Ascent Kinetics podcast by Treeline Endurance, where we explore the new science of exercise for health and performance. We'll keep it short and sweet and should fit everything in before the end of your commute. I am your host, Greg Marshall. I'm a coach, educator, and researcher. I've helped athletes build all the way from zero fitness to huge feats of athleticism, a journey that I myself started on 13 years ago. The content covered here is an expanded audio format of the content appearing on our blog at treelineendurance.com. Today's topic is misconceptions around mitochondria and mitochondrial density, as well as a look at some of the new science on what they mean for both health and athletic performance. I've been working with athletes for about 8 years now, and in that time, I've done a lot of thinking about what a coach needs to be able to offer the athletes that they work with. The coaching landscape's changed a lot in the last 20 or 30 years. We've sort of moved away from the coaching philosophy that says you should punish athletes for, say, not performing well on a workout by withholding water, things like that. There's an expectation, I think, that coaches need to look like they lead. They have to present the sense of a leader, and they have to provide strict guidelines for the actions that the folks that they work with take on. I think part of this comes from the sense that we need to be useful as coaches. If people are trusting us with their time and their energy, then we should prove to ourselves as well as to them that we're doing enough by giving a lot of guidance. Some coaches intently take that idea into practice, and it becomes part of their philosophy on coaching. And it's really up to the athlete whether they adapt to the coach's coaching style or not. But I think that in truth, a good coach is one that lets the athlete lead 90% of the time. The social media image of a coach isn't representative of how the coach-client relationship should actually work. There are times when the coach guides because the athlete's looking for guidance from the coach. And there are times when the coach must know to guide, even when the athlete's not explicitly looking for guidance from the coach. But by and large, I think the coach's job is to be the one asking. They should listen. The person in front of them is the one who does the growing, and nobody is going to bring that growth to fruition except for that athlete. Coaching is allowing that to happen, watering the seeds only when they need it. Knowing when to water and exactly how much to give is the skill. Good coaches are among the first to know when growth is happening. One of the challenges that we all face is the ability to zoom out our perspective and sort of see the growth that we're all going through. But that's what a coach is there for, is to help us zoom out and realize how far we've come. We focus on the task that's in front of us. It's human nature. Not just that, but we're aware of every mistake we've made on the path. All of those things distract us, and we forget where we started. The coach takes on the challenge of helping us to remember the larger context when we instinctively turn our attention to that next obstacle. The coach creates a safer space for exploration on an athlete's own time. It has to be on the athlete's own time, because that's the only way that the lessons will ever really stick for the long term. Anyway, I'd be curious to hear what you envision when you think about the image of what a coach does. If you're a training endurance athlete, then you've almost certainly heard of the 80-20 rule. It was initially observed by Dr. Steven Seiler and later became the name of a popular endurance sports training company. The rule, which again really was more of an observation initially, was that elite athletes across sports tended to average about 80% of their training time at low intensity, meaning an effort that they could sustain for many hours straight while chatting with a friend that was riding along next to them. The other 20% of the time was at moderate or higher intensities, meaning no longer the comfortable, I could do this all day sort of feeling that the 80% required. The 20% requires focus and a bit more willingness to persist against discomfort. But the fitness return on that investment from that kind of work relatively is quite high. The idea was given the 80-20 name, but that ratio isn't necessarily set in stone. Folks who adhere to this training philosophy might get up to 70-30 or down to a 90-10 split in any given week. If athletes go beyond that general range for very long, issues tend to crop up. Overtraining occurs when athletes continue to complete hard sessions, but the physiology plateaus or even regresses in response to that work instead of improving like we'd expect. Science still has a lot of questions to answer about exactly what causes the body to stop responding to training positively and how to turn things around. It's relatively easy to walk out of overtraining, but something called overtraining syndrome is sort of the more extreme brother. And based on reports, it's much harder to recover from, if it's even possible. Some athletes struggle for years with overtraining syndrome. Our topic for this week might explain one issue in this very large question of training versus overtraining. For years, endurance athletes have been told that the key to sustained aerobic performance is training that stimulates something called mitochondrial density, the number of mitochondria that are present inside of a muscle cell. A new paper in the journal Cell Metabolism puts that question to the test. Is having more mitochondria always better for health and performance? Maybe you remember mitochondria, the powerhouse of the cell. If there's only one cellular component to credit to generating the energy that our cells use to live, mitochondria makes a strong case for that title. Essentially, mitochondria take in oxygen, carbohydrates, and fats and spit out the closest thing to molecular energy that the cells of our body can use, a molecule called adenosine triphosphate, or ATP. That's happening in pretty much every living cell in the body. If you're seasoned in training for endurance performance, some faint memories are probably boiling to the surface if your coach sharing with you at some point that all of those runs are stimulating cells to develop a greater mitochondrial density, more mitochondria inside each muscle cell. More mitochondrial density, faster energy production by muscle cells. Faster energy production by muscle cells, better performance. The implicit assumption is that all of the mitochondria are created equal. If one mitochondria can make, say, 200 ATP molecules per minute, we sort of treat the trillions of mitochondria in the body with the assumption that they all make about 200 ATP molecules per minute. And that's sort of where we pick up. A researcher named Mikael Flockhart and his colleagues at the Swedish School of Sports and Health Science decided to actually put this assumption to the test. The author writes, the quality of the mitochondrial population and its effects on metabolic health is not merely regulated by the mitochondrial number and its respiratory capacity. An emerging field of research has shown that the location and function of mitochondria within the cell is highly dynamic and regulated by fusion and fission events, creating a large communicative mitochondrial network. In many pathological states, mitochondria display a reduced ability to respond to nutrient supply and match mitochondrial respiration to metabolic demand. Flockhart argues that the mitochondria aren't just drones on duty. They're more like an elementary school child at the lunch table. Sometimes they're really hungry, sometimes they're not. Sometimes they might be feeling stubborn and choose only to eat fats or carbs, even if it's not actually what's in their lunchbox. Their appetite might even be influenced by whether or not they're sitting with their friends at the table that day. The environment around a mitochondria influences how useful it actually is, just like the environment around an elementary school child might influence how much of their lunch they eat that day. Okay, so mitochondria are a little bit flaky. If not all mitochondria are the same, then what exactly do the bad ones look like, and how do we avoid them? The study was set up as follows. 11 participants, 6 females and 5 males, completed a 4-week training protocol of ramping intensity volume on an indoor bike trainer. To keep the results of the study more clear-cut, there were only 2 workout formats used for all of the quote-unquote hard training sessions. Those were a 5x8 minute ride or a 5x4 minute ride, both with a 3-minute rest interval between each hard interval. One session was twice as long as the other, but the point of the sessions was the same. Empty the tank. Hit the fastest pace and the highest effort you can for every interval session. Each week of the protocol, athletes did more hard sessions than in the prior week. In the first week, they did a total of 36 minutes of hard riding. In the second week, they did 90 minutes of hard riding. And in the third week, they did 2.5 hours or about 150 minutes of hard riding. The fourth week, researchers wanted to allow for some recovery, so the intensity volume drops back down, back to about 50 minutes of intensity. Throughout the study, researchers collected muscle tissue samples from the quad muscles of the volunteers to assess mitochondrial density and the function of the mitochondria in those muscle cells. They also ran several glucose tolerance tests to understand how the athletes' bodies responded to sugar ingestion as training load shifted from light to heavy. A glucose tolerance test is done by feeding some sugar and then watching blood sugar. Normally, the body should combat prolonged elevation of blood sugar. So what did they find? Well, in the most aggressive training week, where athletes underwent 2.5 hours of intense training, mitochondrial density increased in muscle tissue samples. But each of those mitochondria in the sample was comparatively weaker or less functional. The total energy produced by the large number of mitochondria ended up being essentially the same as before there was a larger number of mitochondria. So even though we had more mitochondria, they're not necessarily doing the athlete any good. Versus if we compare that to the mitochondrial changes in the week with moderate training, in other words, the week where they did 90 minutes of hard training rather than 2.5 hours, there was still a slight increase in mitochondrial density in the 90-minute training week. Not as much as in the 2.5 hour week, right? But each of those mitochondria was still more functional. Okay, that's interesting. But what happens if after a week of super intense training, we allow a period of recovery? If we dig a super deep hole, creating a lot of fatigue for athletes, but then we allow those athletes to rest, do they come out the other side stronger than if they just did moderate training? And it looks like the answer to that question is no. Only some of the mitochondrial function was restored after a week of rest. The overall healthier mitochondria still appeared in the sample after the 90-minute intensity week. If we zoom out, the mitochondria that are produced under that period of extreme strain don't look like they're improving fitness. They look more like they're a coping mechanism against extraordinary strain. That sounds an awful lot like the difference between functional and non-functional overreaching. The point of training is to strain the body, but the point is only realized as the body gets stronger in response to that training. The mitochondria produced in the hardest week of training of this study look like one possible factor in non-functional overreaching. The dysfunction in mitochondria has wider implications for our health. Mitochondria get fuel from the blood. The blood delivers fuel in part as glucose. If mitochondria are bad at taking up that sugar, then sugar is going to continue to hang out in the blood. Too much sugar in the blood, cardinal symptom of metabolic syndrome like diabetes. And that's exactly what the researchers found. The glucose kinetics of athletes looked as bad as a type 2 diabetic after the hard training period, and the athletes had only partially recovered from that by the end of the recovery week. So where does that leave us? Training hard from time to time is still a surefire way to build better health and fitness in a hurry. The bottom line is that you can do too much, and now we have a better idea of exactly what that might cost us. What Flockhart's team shows is that there's more to lose than to gain if we're doing all-out intervals every day or every other day. Most athletes aren't training that way, but now we have a better idea of what it could cost us if we are. Mitochondrial density is great, but it only works if those mitochondria are strong and healthy for the longer haul. This study was somewhat of a breakthrough in showing that mitochondria are complicated, and that's why we're covering it. The problem with answering new and complicated questions is that even if we manage to describe something successfully like Flockhart and the colleagues did with this paper, it's just that setting the stage for more questions. This was a 4-week intervention that had the same participants spend a week in each of the training phases. One question I had reading it is what would happen if we broke those training phases up with a recovery week, putting a week of recovery after the 90-minute hard week and then another recovery week after the 2-hour and 50-minute week. Maybe mitochondria can recover more effectively then. I'm not sure. But if you're someone who has trained for or is thinking about training for an endurance event, doesn't really matter whether it's a 1-mile run or marathon or an Ironman. I have the following question. You've got a normal week of training planned for this week. Your training for next week looks similar, but you just had work travel or parenting duties thrown on your schedule for next week. You know you're not going to be able to get all of the training in as is currently planned for next week. So, do you choose to move the extra training into this week, or do you just chalk it up to lost time? Let us know in the comments. If you enjoyed this episode, you can show your support by sharing it with a friend or training partner and by giving us a quick rating on the streaming service of your choice. You can also sign up for our newsletter at treelineendurance.com to receive our monthly review and other exclusive content. If you want to take your support to the next level, you can contribute at the link in the show notes. This goes a long way towards helping us bring more insights on the science of exercise for health and performance. This podcast is brought to you by Treeline Endurance. See you next time here on Ascent Kinetics.